Now that we have laid out the basic principles of Snell's law, and we've seen the way that light rays bend when they pass from one transparent material to another, we will be able to model the behavior of light as it passes through simple lenses, typically made of glass or plastic. And the textbook, chapter 34, lays out the rules for this behavior of the light interacting with lenses. We call this geometric optics, and we'll deal with two basic types of lenses. The first we call converging, and you can identify these lenses because they're thicker at the center than at the edges. There are different shapes of lenses that represent all the same basic category of converging. The most common that we'll run into is called a biconvex lens. So if you imagine just a center line here, then both edges bulge out to give you a lens that's thicker at the center than at its edges. You could imagine also having a flat side with one convex side. This is called plano convex. Okay, still thicker at the center. And there's a type which is reminiscent of a contact lens, if you will. This is called a meniscus lens. Again, still thicker at the center than it is at the edges. All three of these will converge distant parallel light rays down to a single point. So the behavior is such that if we send in light waves, that are modeled as these linear rays, as we've done throughout the early optics discussions. We know that it's a reasonable approximation to say that distant light sources give us parallel incoming light rays because they will not diverge much. The sun is the prime example of this. Light rays that are coming to us from the sun that hit an area as small as a lens are going to be so close to parallel that you might as well just call them. So they're called converging because there's a single point here, we'll call it the focal point, where these parallel incoming light rays will converge. Here's one passing straight through. Just a few more to really drive the point home. These all converge at something called the focal point. And if our distant object is extended, meaning there's light coming from different locations on the object, each location on the object itself will have a corresponding point on what we call the image plane. So in this example, you might say our distant object is the sun. Our image plane will contain a small extended image of a sun. I'm only illustrating the convergence of rays from one location on the sun. It appears to have some angular extent on the sky, and that would be mapped to the plane here. So this was the first type of lens, the converging lens. The second type of lens is called diverging. And you can spot these because the lens is thicker at the edges than at the center. Just like with the converging lenses, the diverging have a few different common shapes. The one that we will use most often is what we call a biconcave lens. Where both sides of the lens are caving in towards the center line, and it is thinner at the center than it is at the edges. Just like before, you could also imagine a plano concave lens, which would do something like this. Also thinner at the center. And then there is another type of meniscus lens, which has to have curvature on both sides, but here one face will have a greater radius of curvature than the other. So maybe some very large radius of curvature here, with a smaller radius of curvature on that face. So it's another type of meniscus lens. You can see that the plano concave is just a special case of the meniscus lens. When this large radius of curvature goes to infinity, you just get a flat surface on one side. Okay, so diverging lenses, what do these do to our incoming light rays? Again, if that distant object is our source of parallel light rays, maybe the sun again. That first one is easy, it's always passing right through the center, but how will the others behave? I'm going to reduce the number that I draw here for the sake of time. Get 2 on each side. These parallel light rays are going to bend when they leave the lens on the right side here. And they'll follow a path which appears to be emanating from a common location. Even though these light rays are diverging, they're all traveling apart on the right-hand side of the lens. They look like they're coming from the same spot on the left side. I'll use dashed lines to the left of the lens here because it's clear that the light rays are not actually traveling to or from that special point, but they appear to emanate from that point. And if you were an observer out here, and you use the special converging lens in your eyeball to focus these diverging lenses down onto your retina, you are going to envision an image which is here. So this is your image plane. So your image of that distant object will appear to be on the far side of this lens, but much closer to you than the distant object appears. The label of thin lens, this is the type of lens that we're going to use exclusively in this course. A thin lens does not translate light rays laterally enough to introduce large errors. Or another way of saying this is the thickness of the lens is small compared to its radius of curvature. Practically speaking, you can imagine if you, say, go back to your standard biconvex lens, you can have a light ray come in. You know that there will be refraction at that surface. If we're going, say, from air to glass, the light must bend towards the normal line. Okay, it's that normal extended on into the lens, and an even smaller angle on this side. So that light will travel across the lens here and re-emerge, bending back away from the normal on this side. You can see what has happened here. The light ray, if you hit these parallel faces right at the center of the lens, the light ray will pass through with essentially no lateral displacement this way. And you can remind yourself to go back to page 208, problem 7, where you practice drawing the rays passing through a piece of glass that's flat on both sides. And that's giving us our first clue towards the next video, where there's a one special location on the lens where light will pass through without changing directions. The take-home point with thin lenses is that we can model they act as if all bending or refraction occurs at the center. So in our diagrams, we will not worry about trying to refract the light once here and then propagate through the glass and then refract again when it hits the air. We're going to model the behavior as if it just bends once right at the center of the lens. In the next video, we'll take a look at principal rays for determining the location of an image.